Hello everyone. In this question, we are going to evaluate a surface integral. So we've got a integral over a certain surface. In this case, it's an upper hemisphere, which is like the top part of the sphere. So the equation of it is z equals 36 minus x squared minus y squared. And we're integrating z ds. Okay, so what we're doing first is we are computing what's called the differential over the surface, so ds, and the formula for that is square root of 1 plus gx. Now, when I say gx, this means partial derivative of a function g of x and y, and then we square that plus partial derivative with respect to y, and we square that. Now, what is the function g? Well, we are assuming that our surface is represented as z equals g of xy. So this is g of xy right here. That's the square root. Okay, so first we have to simplify it. So let's see if we can compute the differential and simplify it. Okay, so first, what is g with respect to x? Now, we have square root of something. And you should know that square root of something derivative is 1 over 2 square roots of the same exact something. So it's not, so don't put the derivative inside the root. It's just 1 over square root, the same exact square root. Multiply that by the derivative of the thing, quote unquote, whatever the expression is inside with respect to x. Now let's look at it. Derivative of 36 is 0 because it's a number. Then we have minus. Derivative of x squared is 2x. And derivative of y squared will be 0 because y squared does not have an x. Okay, now we can simplify this further by just canceling the 2 over here and over here. So the final answer is going to be negative x divided by that square root. That's gx. Now, the gy, I'm not going to go over the same process again because it's going to be the same thing, but just a y in the numerator. So this is just square root of 36 minus x squared minus y squared. Okay, so now let's simplify the expression under the root in ds. So what is 1 plus gx squared plus gy squared? Let's see what that is. So we're doing 1 plus. Now, what happens when we square a negative? So the negative goes away, and then we're going to get x squared. And on the bottom, the square root is going to disappear because we're squaring a square root. And then we got the exact same thing for gy, so that'll be y squared divided by 36 minus x squared minus y squared. All right, now to simplify this further, we want to bring the whole thing to a common denominator. So we already have the same denominator for the last two. And for 1, we can just think of it as multiply the top and the bottom by the 36 minus x squared minus y squared. So this is what's going to happen, right? Okay, so and then plus x squared and plus y squared. So notice what happens here. So we got negative x squared and positive x squared. That cancels. And then we also get negative y squared and positive y squared. That also cancels. So now we've got 36 on the top and 36 minus x squared minus y squared on the bottom. All right, so what is that going to come out to when we talk about ds? So ds is square root of that, right? So don't forget to take the square root of this expression. Okay, so and then multiply that by dA, which stands for either dy dx or dx dy. So when we take the square root, the top becomes 6, and then the bottom will be the square root. So I'm just taking the square root of the top divided by square root of the bottom. I'm just separating that. Okay, so that's what we need to integrate. So let me put that in here. Okay, so that's what ds is. All right, so let's just submit that. Okay, so this part is correct. Now let's go to the actual computation of the integral. So we are going to be integrating over this surface, but we're integrating z. Now, one thing you need to remember with surface integrals is that your integral, whenever you're converting it to a double integral, should not have any z in it. Because you are on the surface, like you are integrating over the surface, and on the surface, z equals that square root. So wherever you see z, you just immediately should substitute whatever it is on the surface. So that would be the square root. Okay, and then it'll be ds, but we just got ds, so that's 6 divided by the same exact square root. And notice how the square root here is going to cancel out, which is really, really nice. So there it is. So we are basically integrating 6. So this is a double integral of 6 dA. Now, over what? Well, that would be a good question. Now, whenever you see this x squared and y squared, think of this is going to be a circle. I will probably be integrating over a circle. Now, what you're supposed to integrate over the projection of the surface onto the xy plane. But what is the projection of the upper hemisphere on the xy plane? So what does upper hemisphere looks like? So you've got, so imagine this is a 6, for example, and you've got this hemisphere here. This part you cannot see, and let's say this is also a 6 right here, right? And so then that's going to be that hemisphere, upper hemisphere. All right, so what happens when you project it? What does that mean, project? So you take that hemisphere, that head, and you basically make every single point on that head be the same x and y coordinate, but z coordinate will be 0. So you're like flattening it out. Imagine, dropping a brick on that surface. What you're going to get is this circle, right? The circle on the xy plane with radius 6. So we are going to switch to polar coordinates from here. How do we switch to polar coordinates and how do we integrate over the circle? So first of all, our integrand, which is 6, will get multiplied by r. And then you're going to get dr d theta. So integrating over the circle is very simple. The outside limits should be 0 to 2 pi because that's a whole circle. And inside limits should be 0 to whatever is the radius of the circle, right? So the radius of the circle is 6. So that would be 0 to 6. And so that's what we're going to be setting up here. So let's just type that in here, 0 to 6. And the reason why this extra r appears, which was not there before, but suddenly it appears, is because we are switching to polar coordinates. So anytime you're switching from rectangular to polar, you're gonna get an extra r, which is called the Jacobian. So switch to polar. Because of that, you get this extra r. Okay, so that's that. Now, computing it, there are actually two ways you can think about it. You can actually compute this integral over, let's just say this is region is D, by knowing just the properties of double integrals. So notice how 6 can be pulled out, and then you are just basically integrating 1 over the circle. Okay, now what does that mean, integrate 1? This integral of 1, double integral of 1, is just the area of the region. Now what is the area of the circle? Everybody knows what it is. So let's see if I can just move the picture a little bit further. Oh well, it didn't quite work out, but okay, hold on. Let me just erase this. Okay, so what I was going to say is this is just going to be area of the circle, but area of the circle is pi r squared. So that would be pi 6 squared. So it's going to be 6 cubed, so 216 pi. Now, let's show that that is going to be the same thing if we were actually evaluating it without knowing the properties of double integrals. So because the integral doesn't have a theta, we can just basically split it into just the 0 to 2 pi d theta and then 0 to 6 r dr. Notice that we can always split an integral if the integrand, or whatever we're integrating, is a product of something that has one of the variables times something that has the other variable. And that's what I'm using right here. Also, the limits must be numbers. So if any of the limits had, let's say, an r or in it, that's not okay. You cannot split, then you would have to integrate regular, like a partial integration. Okay, but anyway, the first part is just 2 pi. The second part is 6r to the power 1. So that would be like 6 over 2r squared. So that would be 3r squared from 0 to 6. And then we get 2 pi. And then we multiply this by so 6 squared, that's going to be 3 times 36. Okay, so that should be the same that what I got over here. So let's see. Let me just compute that. So 2 times 3 times 36, that's also going to be 216. So either way, I'm getting 216 pi for this problem.